This is Math 2020, and today we are doing lecture 36, which is section 11.6 of the text. The title of the section is called Absolute Convergence. 11.6, Absolute Convergence. With the exception of the alternating series test, which only applies in the case of alternating series, we have very few tests available to us so far which test series with non-positive terms, for example, series with negative terms. So what I'm going to talk about today is a technique, a set of tools for studying series with possibly negative terms. Okay, so let sigma a sub n be a series. Now we could also associate to this another series, which is the series of absolute values, so the absolute value. So this is a series with non-negative terms. Okay, and we make a definition. We'll say that the original series, sigma a sub n, is absolutely convergent if the associated series of absolute values is convergent. So let me give you an example of such a thing. So example is this. Let's consider summation minus 1 to n over n, 1 to the n over n squared. So the series of absolute values in this case is the series, if we take the absolute value, the signs go away. You get 1 over n squared. And this is the 2 series, and it converges. So the series, summation minus 1 to the n over n squared, is this series is absolutely convergent for that reason. On the other hand, we can consider the example summation minus 1 to the n over n, or maybe 1 minus 1 to the n minus 1. It doesn't matter. So then the series of absolute values is 1 over n, and this is the harmonic series, and this diverges, which tells me that this series of the alternating harmonic series, this series here, is not absolutely convergent. But it does converge, even though it converges by the alternating series test. So we could, this actually leads to a definition that I'm going to make now, which is a weaker definition than absolute convergence. So here's a definition. A series, summation a sub n, is conditionally convergent. Conditionally convergent if it converges, but not absolutely. And the example that I just gave, the example summation minus 1 to the n minus 1 over n, is conditionally convergent because it converges by the alternating series test, but its series of absolute values is harmonic, which diverges. Okay, so we have the notion of conditional convergence, and we have the notion of absolute convergence. Okay, so here is a fact that's important to mention. Here's a fact. If we have an absolutely convergent series, then the series actually converges. And I'm going to explain the reason for this fact. The reason for that is that that if this is true, if sigma a sub n is absolutely convergent, that means that the series of absolute values converges. But notice that a sub n plus its absolute value is at most twice the absolute value of a sub n. It's equal if a sub n is positive, and it's strictly less than if a sub n is negative. You get 0 in that case. And in fact, we get this bound here. And moreover, what this tells us is that since this series converges, the series of absolute values, that will imply that twice the series converges by one of the properties of series I mentioned. And therefore, this series, therefore by the comparison test, the series a sub n plus its absolute value converges. And now by the another property, if we have two convergent series, we can subtract one from the other to get a convergent series, and that will imply that summation a sub n plus its absolute value minus a sub n, that series converges. Oops. But then what is that sum? That's the sum a sub n. This is equal to a sub n. Converges. So we just showed what we had to show. We had to show that if a series absolutely converges, then the series actually converges. Okay, so absolute convergence is stronger than convergence, is a stronger property. So in summary, so far, absolute convergence implies convergence. But the other way around is not true, as we saw with the alternating harmonic series. Okay, so that's the only theoretical part of this section. I want to now get to the tests. So, so here are some tests. They're going to introduce two tests. One is called the ratio test, which is extremely useful. It's the ratio test for absolute convergence. So you have a series, sigma a sub n, and the ratio test says this, okay? And there's no condition on the series whatsoever. So we look at the following thing. We take the nth plus first term of the series, and we divide it by the nth term, and we take the absolute value. Okay, and we take the limit as n approaches infinity of that expression, and we'll set that equal to some L, assuming L is a number. And then the statement is, if L is less than 1, the series absolutely converges. Absolutely converges. If L is bigger than 1, summation A sub n diverges. And let me write summation A sub n in the first line also. And if L equals 1, the test is inconclusive. You can't say anything with the test. The test is not good enough to say anything. Okay, so that's the ratio test. This is an important result. I'm not going to prove it, but we're going to be using it over and over. So let's do some examples with the ratio test. Here's an example. Summation 1 over n factorial. Now, I believe we actually handled that. By the way, if the series has only positive terms, then absolute convergence and convergence are the same property because your absolute value is not changing anything if you have positive terms. So let's look at 1 over n factorial. If we use the ratio test, we're going to get a n plus 1 over a sub n. That's the same as 1 over n plus 1 factorial in the numerator. And we're going to divide it by 1 over n factorial in the denominator, which is the same as n factorial over n plus 1 factorial, which is 1 over n plus 1. Now, as n goes to infinity, this tends to 0, and that's our L. Since L is less than 1, we see that the series converges. I don't have to say absolutely here because there's no extra information in the word absolutely because the series is a series with positive terms. Here's another example. Summation minus 2 to the power of n over n squared. Now, we can handle this, it turns out, by the alternating series test, but I think it's easier to deal with this with the ratio test. So we're going to use the ratio test. Not the alternating series test, the divergence test. This is going to diverge. We'll see that right now. So what is a n sub n plus 1 over a sub n? Absolute value. Well, that's the absolute value of negative 2 to the n plus first power divided by n plus 1 squared times the reciprocal of a sub n, which is n squared over negative 2 to the power of n. And what do you get? There's a lot of cancellation here. This is the absolute value of negative 2 times n over n plus 1 quantity squared. And we can bring the negative 2 out to make a 2. So let me do that right away. And so this is twice n over n plus 1 squared. Now what happens to n over n plus 1 as n goes to infinity? This term goes to 1, so the entire expression tends to 2. That's L. L is bigger than 1, so the series diverges. Okay, so that's cool. Let's try another one. How about the example given by summation n factorial over n to the nth power? Now, we actually looked at, this could be done in other ways also, but it's easiest by the ratio. It might be considered easiest using the ratio test. So a sub n plus 1 over a sub n, absolute value. Well, it's a series with positive terms. You're going to get n plus 1 factorial over n plus 1 to the power of n plus 1 times the reciprocal of a sub n, which is n to the n over n factorial. And this simplifies a lot because n plus 1 factorial over n factorial is n plus 1. And we're going to get n to the n over n plus 1 to the n plus 1. And a factor of n plus 1 on the top cancels with a factor of n plus 1 on the bottom. And you're going to get n over n plus 1 to the nth power. Now, I stared at this a little bit to see what was going on. And it's one way to study this is to think of this as 1 over the reciprocal of that fraction to the n. So it's n plus 1 over n. I'm sorry, not that. it would be, let me say it this way. Oops. Yes. What I'd like to say is this is the same thing by just ordinary algebra, 1 over n plus 1 over n to the nth power. And I can rewrite this as 1 over 1 plus 1 over n to the nth power. Now you see what's going on. One of the definitions of the number e is the limit of this denominator as n goes to infinity. So as n goes to infinity, the bottom tends to the number e, which is about 2.7. So this is 1 over this limit. This tends to 1 over e, and that's our L. And 1 over e is less than 1, so the series converges. We don't have to say absolutely because the series is positive terms by the ratio test. So that takes care of that. So there's another test called the root test, which is also a very useful test that I will be discussing. And this is best applied to the case where the nth term of the series is an nth power. So this will be applied when the nth power occurs in the nth term. There's no guarantee that it's going to work, but this is just suggestive of what to do. And the statement is this. So the statement of the root test says that if we take the nth root of the absolute value of a sub n and take the limit as n tends to infinity of that and call it L, then the outcome is just like in the ratio test. If L is less than 1, the series summation a sub n absolutely converges. If L is bigger than 1, it diverges. And if L equals 1, the test is inconclusive. Okay, so let's try to apply this in certain situations. Here's an example. How about the sum of n squared plus 1 over 2n squared plus 1 to the nth power? N goes from 1 to infinity, say. Okay, so a sub n is n squared plus 1 to the nth power over 2n squared plus 1. Oh, I'm not writing that correctly. It's n squared plus 1 over 2n squared plus 1 to the nth power. So the nth root of the absolute value of a sub n is n squared plus 1 over 2n squared plus 1. Now in Calc 1, you learn that this limit tends to the quotient of the coefficients of the highest power of n that appears here. So this is going to tend to 1 over 2 as n goes to infinity. And that's our L, and L is less than 1, so the series converges. Okay, let's try another one. Let's try the sum of n over ln of n to the nth power. Now we have to start here with n at least 2, because if n is 1, you get a vanishing denominator in the ln. Okay, so how do we do this? Well, a sub n is n over ln of n to the nth power. So the nth root of that absolute value of a sub n, which is going to be given by n over ln of n. So we have to see what's happening to n over ln of n. So I suggest we look at x over ln of x, the function f of x, and we want to sort of understand what happens to this as x goes to infinity. Well, by L'Hopital's rule, this is an indeterminate form of type infinity over infinity. This is the limit as x goes to infinity of the derivative of the numerator, which is 1, over the derivative of the denominator, which is 1 over x. But that's the same as the limit as x goes to infinity of x, which is plus infinity. So it diverges. This is our L. This tends to plus infinity. So the series diverges. That's what we get from that using the root test. Okay, I'm going to do one more just to show you can get things which are inconclusive out of the root test. So here's an example. The sum of n squared plus 1 over n squared plus 2n, and that's all to the nth power. So the nth root of a sub n, absolute value a sub n, is n squared plus 1 over n squared plus 2n, and that tends to plus 1 when n goes to infinity. And so this is our L, so the test is inconclusive. If you want to see what's going on with this, we have to use a different method. And as far as I know, we don't have a method to study this yet. Okay, so that's all for the ratio and root test and the notion of absolute convergence. And so we're done with this section.